是有一张，
对，还有一张
对吧？OK。
虽然available 就是只有这些嘛。
对对对
OK。
然后如果让他们扫母体可以选的时候，这边就会下放下来。
这里才下来，对不对？所以也就他们先选这些，他们知道的。
除非他们不是reject到，
所以这个才会下来嘛，对不对？对，16才会下来，要照顺序吗？还是
没有，就是一次下来，就是比如说现在一个下来16，然后后面下来就是11跟2一起下来。
哦 ，OK， 是到对点。
对，没有自我，我觉得是不能选。
好，那我们会准时开始，都是2点准时开始。
但是他不会，他会。
Okay, so okay, be quiet. Now, okay, let's start our competition. Firstly, yeah, let's introduce our juries one by one. So maybe from Professor Chen. Okay, you won't say something. You can say your name and I'm sorry.
Hi, I'm Chin Chen. I'm from National Paranormal University.
Okay.
I'm Lian Hong from Chinese Media Academy. Thank you. Chung Wan from National University.
TYPT S603 University.
Okay, so I'm the chair of this section. So my name is Yan Wing Lan. I'm from this campus, National Taiwan Normal University. And then now let's start to introduce your team and your team member. So let's start from the okay 火箭3人组.
Okay, so this first time that we in the competitions. So my name is Eugene and Gary and this is Amber. Thank you.
And then a reviewer.
And I'm the captain of Team Excel here. My name is Chen Xuan, and she is Wu Fangjie, she is Chen Jihan, and he is Lin Kaizhe and Chen Taihong.
Thank you.
So we're Team 1 of Perspective American School. I'm Captain Ethan Wu. This is Group 1. This is Hamilton Grove. This is Isabel Lin, and this is Sean Lin.
Okay, thank you. Okay, now let's start the competition. So firstly, the component that is the challenge the province. 14. 14.
We would like to accept the challenge.
Okay, accept.
Accept, right?
Yeah, accept. Okay, so please write down your name on the paper. Yeah, at that time now is the preparation time for the poker. Okay, so start with presentation.
My name is Tom Cool and I'm presenting topic 14, rule trick for all-nighters. According to the problem statement, place a ruler that extends over the edge of the table and drop a ball at its free end. A simple piece of paper can withstand the force of the ball onto the ruler and keep the ruler on the table. Investigate how the force output depends on relevant parameters such as ruler length, area of paper, and the ratio between the hanging and non-hanging portion of the ruler. I'll be focusing on how each parameter impacts the force output and how each parameter relates to each other. This is a breakdown of my presentation. To explain the phenomenon, if I were to place a ruler across on the edge of the table, upon hitting it with a ball, it should provide a sufficient amount of force to hit the ruler off the table. But if I were to place a paper over it, it would provide enough force to keep it on the table. This can be explained by when, upon hitting the ball hitting the ruler, it increases the height of the paper and increases the volume underneath it. But because air cannot rush in to fill in the increased volume, it would create a vacuum, allowing the atmospheric pressure to push down on the paper and keeping the ruler on the table. To model this, I equated the torques on both two sides of the non-hanging and hanging lengths of the ruler. And here's just a breakdown of it. I equate the torques of the two sides and multiply both sides by delta T, the contact time between the ruler and the ball. And then this allows me to equate the hanging side to the impulse of the ball and the non-hanging side to the sum of forces on the ruler, which is the weight of the paper and the force by the atmospheric pressure. The force by atmospheric pressure can be equated to the change in pressure, which I equate to the change in volume beneath the paper. I take out the assumption that the initial pressure underneath the paper is equated to the atmospheric pressure. For the experiment setup, I place a simple acrylic ruler across the table and place a paper on top of it. To drop the ball, I drop it through a short tube that is attached to a stand or a wall to give some consistency to how I drop the ball. And then I place a camera from the side profile to record the phenomenon. And according to the model, this is a list of all the parameters that would be relevant to the phenomenon. And the parameters I'll be varying is the paper area, the ball, mass of the ball, the ratio and of the ruler lengths, and the ball drop height. And upon each trial, I'll be measuring the dimensions of the air pocket underneath the paper, the maximum height that the ruler attains, and the contact time between the ball and the ruler. So I'll be breaking down the observed behavior. Upon the ball hitting the ruler, it would increase the height of the paper. And with this, I observed that the ruler receives a restoring force on its opposite end, lifting it upwards before falling back on the table. In a situation where the ball does provide a sufficient amount of force to take the ruler off the table, upon lifting up the paper, instead of receiving restoring force, it simply continues to fall off before falling off the table. Since there's a restoring force observed on the hanging end of the ruler, there must be a force downwards exerted by the paper on its other end. So this means that the change in volume I'll be looking at is between the first and second step as observed in the behavior. So with this in mind, I can begin making some predictions on the parameters I listed based on observation and the model. First of all, I predict that the area of the paper will not have an impact on the force output. This is because that when decreasing the area of the paper, the ruler would have to reach a higher height to obtain the same amount of volume underneath the paper to ensure the force necessary to keep the ruler on the table. So I believe that the increased height will cancel out the effect of the area of the paper. Looking at the length of the ruler, I believe increasing both the hanging and non-hanging length will increase the force output. Increasing the non-hanging length will increase the height at which the paper is lifted, and increasing the hanging length will increase the torque that's exerted onto the paper. And finally, increasing the mass of the ball and the drop height will both increase the force output. These parameters will act as sort of as varying the impulse that the ball gives to the ruler. With this, I can begin showing how I calculate the force output. So first of all, how I model the volume under the paper is that I treat it as a triangular prism. However, the prism does not have a uniform height, so I'll have to average the height in order to find the volume. And it's just a diagram to show you how I broke down the shape of the under the paper. I split it into two triangular prisms and calculate the volume of them separately. So through observation, the shape of the paper is in reality a concave down curve. So this means that a triangular prism would be an underestimation. To balance this out, I also calculate a rectangular prism and average the two to get a closer estimation. And I also have to keep in mind to record the volume, the velocity of the ball after colliding with the ruler, as that would be necessary to find how much impulse was transferred onto the ruler. In the situation where the ball does not continue falling down, but instead is deflected upwards, I assume that the impulse is completely transferred to the ruler, since through observation I've noticed that the upward motion of the ball is actually caused by the restoring force of the ruler, rather than the momentum being reflected upwards. And some of the assumptions I'll be taking is, first of all the calculations and use of averaging for the volume, the assumption with the change in momentum, and assuming the initial pressure underneath the paper as atmospheric pressure, and ignoring the air resistance of the ball for simplifying calculation. So this graph, first of all, compares 2 points. The calculated impulse looking at the change in volume, and the threshold impulse caused by the calculated velocity and mass of the ball. And you can see that the orange dots representing calculated impulse are always above the threshold impulse, which implies that my calculations does show that the paper can provide enough impulse to keep the ruler on the table. And with this graph, I'm showing how I vary the parameters. So first of all, I varied the area of the paper while varying the non-hanging length and the mass of the ball that collides with the ruler. First of all, you can see that increasing the non-hanging length will increase the force output, and there doesn't seem to be much of a consistent difference between increasing the mass, and there's a slight decrease in force output when it comes to increasing the area. And this graph shows what would happen when I would vary the hanging length. And this graph contradicts my initial prediction, which was that increasing hanging length will increase output. Well, over here, so it shows that it decreases output. To explain this, to look deeper into this, I reviewed the footage of the ball colliding with the ruler, and discovered that the average contact time between the ball and the ruler is longer when increasing the hanging length. So this means that the ball is having a harder time moving the ruler upwards. So this implies that increasing the hanging length will sufficiently increase the moment of inertia of the ruler, that it would be more difficult for the ball to push up the ruler, thus making a smaller increase in volume. It can also explain why a larger area is needed to keep the ruler on the table when it has a longer hanging length, as the longer hanging length will not be less able to increase the volume, and thus we need a larger area. So earlier I also showed in the data, I showed you how the mass, there doesn't seem to be much of a consistent difference in mass. So I also again looked at the minimum area needed to keep the ruler on the paper. So keep the ruler on the table. And you can see that there is a difference, so this implies there must be some form of difference. So instead I looked at the difference between the area of the paper and the maximum height attained by the ruler, and this shows a more obvious difference between increasing the mass, which shows that increasing mass does increase the maximum height. And I compared the maximum height to the force output, and this one shows that there is a slight increase in force output as I increase the area, as I increase the maximum height. So this supports my prediction that increasing the mass will increase the force output. However, the problem with this is that this contradicts my prediction regarding area, which I predicted that it won't have an impact on the output. So an explanation why there might actually be an impact on the output by the area is because that when increasing the area, I can before would increase the maximum height. Decreasing the area would increase the maximum height. This would cause a greater vertical stretching of the paper, reducing the horizontal area for the atmospheric pressure to push the ruler onto the table. So this requires a greater change in volume and thus a greater force output. And finally, to verify this one more time, I also vary the drop height, which should affect the phenomenon in the same similar manner as mass, and also shows that there's a difference between the higher drop, which would have a greater velocity, greater impulse transfer. So in summary, looking at all the parameters I predicted, 3 which were proven correct, with area shown to have my prediction on area and hanging length being contradicted. So looking at error analysis, one of the largest sources of error I would have in this experiment is calculating for volume, which, as you remember, I took on many assumptions with. So a way to reduce the errors with this would be to add more camera angles and increase in precision to better measure the dimensions of the air pockets. In fact, one of the better camera angles would be a downward perspective to directly look at the size of the air pocket, but the difficulty with this is that it's hard to differentiate where the air pocket is. And there are some alternatives. There are some alternatives, and rather than just measuring the dimensions of the paper, is to look at some other parameters in the experiment, such as looking at the downward deflection of the ruler and using trigonometry to estimate how high the ruler is deflected upwards. But this would also require some better camera frame rate, and would also have to address certain properties of the ruler and the ball, such as elasticity and vibration. And finally, there's the most important factor when it comes to that often affects impulse. The force output is the exact position and contact time between the ball and the ruler. But this is a little hard. Is quite hard to control, as any time the ball is in uncontrolled free fall could possibly be varied in where it hits the ruler and the contact time to the ruler. So in conclusion, change volume and the momentum transfer to the ruler has the most significant impact to force output, and area of the paper and non-hanging affects the change in volume, and the ball mass, drop height, and hanging length will impact the momentum. However, increasing the inertia of the ruler can be significant enough to negate the increased momentum transfer. And offering some alternative models and different setups can offer some greater accuracy. Thank you.
Okay, so opponent, please ask the question.
So I have like a question about, can you explain why was your data and hypothesis contradictory to each other?
Which ones? I mentioned it for area and hanging.
I want like area.
Area. So initially, I assumed that the maximum height that the maximum height that the paper attains will cancel out the impact of area. But it turns out that since the ruler will be at a higher height, it would have a greater vertical stretch, decreasing the horizontal area for the pressure to push onto the paper. So that would require greater force output to keep the paper and move on the table.
And how can you combat that? This kind of like action is caused by the air pressure, because from your experiment you didn't like prove it that this is caused by air pressure. You just write your ideas about it might cause because the air pressure, and give it like image about how your thing about air pressure will work.
Well, this is I led to this conclusion by mostly looking at footage by reviewing. In which I was looking at footage of the ruler in which the lifting, in which that after colliding with the ruler, there seems to be an area in which the paper, the air it looks like the vacuum underneath the paper collapses, in which the volume underneath the paper collapses and the paper pushes downwards. And mostly the only explanation of this could be the atmospheric pressure, as that's the only force that can be exerted downwards.
Okay, time's up. So preparation time for opponent 3 minutes. Opponent, please take the floor.
Okay, so we are opponents from this round, and we are talking that we're pointed to. So first, the power statement: place a ruler on the edge of the table and draw a bow. Okay, so from this problem statement, we can see from the reporters they have lacking of explanations of the phenomenon. So I think can improve about like say more or more clearly, and investigate the relevant parameters. They have like talked very much about it, so it's good for understanding. And for reporter performance strength. Okay, so they have rich contents with detailed explanations of the calculations and their ideas. And they do list out of many possible assumptions and parameters and detail the error analysis. And about the weakness, they are lacking of the theories and well-known fact to support his claim, and did not explain why the hypothesis was contradictory to the data. And the experiment did not demonstrate the cost of the phenomenon and lacking of the detail of the explanations. And about some questions. Next. Okay, and for error, there isn't enough the evidence to prove the result that they have got.
So you want directly go to the next stage, right? Okay, go to the next stage for the discussion.
Okay, so the first questions I'm going to ask is about do you conduct an experiment that proves the phenomenon is caused by air pressure? So for this question, I'm asking is there have better way to prove it that there have the air pressure? So I mean there is kind of misunderstanding about is it truly air pressure causes, because from the improvement that you are proving.
So experimentally, I couldn't really prove the phenomenon, but there's certain preliminary observations and experimentation. I can prove that it is caused by air pressure. For example, if I were to take the same paper I used to keep the ruler on the table and scrunch it up into a ball and just place it on top of the ruler, the ball would still be able to slap the ruler off the table. So that means that the weight of the paper isn't enough to keep the ruler on the table. So that means the only other force that would be the atmospheric pressure, which can be observed by how the ruler lifts up the paper, and you can see the volume underneath quickly increasing and then collapsing to push the ruler back down. We can show that the only other force that's necessary that can be keeping the ruler on the table is the atmospheric pressure.
And have you tried to change the factor about the ruler and the paper positions to prove it could be a good idea to prove the air pressure? How do you think that?
So you're asking what if I were to change the position of the ruler?
Yes.
So through my observations, I noted that what would be the biggest factor to keeping the ruler on the table is the size is the limitations of the area of the paper. So as long as the paper is still covered on the table on the edges, it will be able to create the vacuum sufficient enough to keep the ruler on the table. However, if I push the ruler closer to one edge, when I push it upwards, that edge, now that being closer to the ruler, might open up more quickly. And as long as one edge opens up, it would allow the air to rush in and not allow the people to keep the ruler on the table.
Okay, so can you go to page 14? 47. From the video you can see that the paper is kind of like flying out through the table. And why still the ruler is staying on the table and not falling?
Okay, so I can break down this video into the photos I showed you earlier, in which so this is the first, so I described in my observations in which I talked about how the ruler lifts upwards, and then the ruler is pushed downwards, such as like this. So you can see that earlier, you can see that the paper is higher on the other end at one moment, and on the next moment it pushes downwards. So that means the volume on this side of the paper has collapsed sufficiently to push the ruler down, and that's why. But then like the other end, but because the ruler receives a restoring force and lifts upwards, it will look like the paper is still floating.
Okay. And next question I'm going to ask is about like table materials. What do you think about like, do the table material really affect the data? Might be a factor that affect it.
I would think the only way that would affect it would be how it handles the edges of the paper. Handles the edges of the paper. Say that like the table is more sticky or has more friction, it might be able to catch onto the edges of the paper more and actually stay closer down, or close it down. Or a more slippery table in which the paper can't really have suction onto the table, it might be able to be lifted out more easily and the ruler would fall off more easily.
So I have some ideas with you that like some kind of like materials of table might be more attractive on the papers and it will cause a increasing forces. So do you have control in this table materials? I mean, you always control in the same tables, so maybe you can it could be a change factor.
And what would you suggest? Like what would I add to the table?
Plastic. Oh, I mean, you can make a graph of this so that we can more understand about does the materials of the table does affect the force that going out, and so you can put it in data so we can understand about does it really caused by the air pressure, because I mean if we change the materials, like some materials is more attractive, and we could know that this have the higher air pressure because the air won't go in, more formulated to go in.
So first of all, you mentioned how you were asking me what kind of trend would be shown if I change the material of the table, and I think it would show a similar trend to changing the area of the paper in which it would affect the maximum height that the paper attains, since it would have to suck in more and gain a higher height in order to keep it down. And onto your point where it says that changing the table, the properties of the table might better prove that its phenomenon is caused by air pressure. I don't think it really affects that, since I don't really think it really proves that, since the air pressure would just be caused by what's pushing down, and the only thing the table would do would be how well it keeps the paper onto the table.
Okay, so for me, I think it do, because it do could prove some of the air pressure it do caused by air pressure. Because I mean, if we have paper that is more attractive on the materials, we can know that the air that when the substance is dropping, the air that go inside the paper will be decreasing. So it could prove that by having the data.
If your objective here was to show that I can change the amount of air that goes into the paper, I think I already sufficiently do so by showing that how different parameters will affect the maximum height attained. For example, earlier I showed how changing the mass of the ball will change how high the ruler goes up. Changing the area will also do the same. So I think that I can already show that more air can rush into the paper and through my other parameters.
Okay, and how can you control the place that the ball falls on the ruler?
So I mentioned that this is something really hard to control. My best way to do so was to put a short tube and attach it to a stand, so that at least when I drop the ball, it would not be varied by on which position I drop it by. But every moment exposed to free fall as it falls from the tube to the ruler, it might just vary a tiny bit and miss the ruler in a different position. So the best way to do so is to ensure that it falls in uncontrolled free fall. But if I were to say put it through an entire tube the whole length, it might impact the friction of the impact. It might be slowed down by the friction in the tube and would affect each time how you apply the ruler.
Okay, so in the factor you have changed the ruler of like the ratio of the rulers that in the table and in the outside of this. Okay, so like I think of that if you change this factor, it will have two factors that will change. First, because like if a ball, we all know like in a balance things, when the side that is longer and the side that is shorter, and we put a stop in the end of the two sides. One side of the place which have like longer length will like become like
I acknowledge that. I acknowledge that in my model, in my mathematical model at the start when I modeled the phenomenon by equating the torque on the two sides, and as you mentioned here, it's like the weight, like you described like a mass, like or a balance. You have the radius which represents R, which represents the two lengths, and how forces on the weight on each side. So yeah, so I did treat it like this, and you can see like that by how I set my model.
Yeah, so I mean, when I change the ratio, they have like two factors is changing. One is like the heavy of like things, just like one say the balance things, and one is the place, the placement in the tables, the longer of the table. So they have like two factors. One is like how long is the ruler that is in the table on table, and other factor is like what is the like just the balance things that if I have like shorter in outside of the table, and it will be harder to pushing up. So they have two factors, and how can you know which affect more?
So that I can usually use that was equivalent to like looking at. Sorry, so you were referring to changing the length of the ruler and how difficult it is to move it.
Yes.
Okay, so there are two ways you can determine this. So first of all is looking at the radius itself, and second, and the other way you want to look at which is how hard to move it is the moment of inertia of the ruler, which also anticipates the length of the ruler. And I did in fact show that how hard the ruler can be moved, it does have an impact on this through this one where I showed that through this data set, which I showed that increasing the non-hanging length, the hanging length does not seem to increase the force output as I expected. In this situation, how hard it is to move the ruler or the inertia mitigates the increased length. So yeah, so I did anticipate for this. So in this situation where the hanging length, it seems that the inertia outweighs the increased length.
Okay, so like the paper, like some kind of paper, because they have different kind of paper too. Do you have change the factor, or what do you think that about the paper will affect it?
I think it would act in the same way as the table, but it would also act in a different way, which is how the shape of the table would be. For example, a more rigid paper would not break downwards in the end and close off a area.
So Kanisa, so upon the quiz summarize.
Okay, so for my questions, they do use many formula. So for my question that I'm asking about, because when I change the factor, and they have two factors like my change, and they do have like say it in the formula, and to prove that. But I think they should like make more understand opinion about like which affects more about it. And just like in the table materials, I'm asking about the paper that fly through the tables. I could see like paper is flying through the table, and white the air go through the might go through the paper, but I still couldn't see the ruler falling down.
Okay, thank you.
And she asked.
So it's time for a reviewer to ask a question for both. So please stand up.
Okay, for both of you, does the shape of the paper affect the phenomenon?
Yes, I think it does. So it affects it by the shape of the paper, the shape of the paper. Or a more
How does it affect?
for example, a more rigid paper, when lifted upwards, might be able to.
I mean the shape. If it cut into a triangle, and what will happen?
So if the
At same area.
so the are you asking how the shape matters?
Yes.
So if the shape allows to make sure that the edges are closed down, it would ensure that the air does not run in.
Okay, thank you. And for the opponent.
So for my place, I think that if in the same areas of the paper, then for like the triangle, it will because many shape will affect a volume. So if in the same area of the things, then some of the shape they will have less volume.
Okay, thank you. And what will the acting time of the contact point affect the phenomenon? Since you mentioned acting time in your report.
So contact time, which is I noted earlier how when the ball collides with the ruler, it sometimes collides with it and takes the ball down, or it stops on the ruler.
Let me ask again. If the contact time is longer, then what will the critical height be?
It would be higher. Because it would also be higher for the contact
Okay,
time.
thank you. And what's your
Can you ask again?
if your contact time is longer, then what will the critical height be like?
You're like.
If the ball contacts your ruler's time is longer, then what will the critical height be like?
Critical height. You mean the ball that bounce out.
Yes.
And the ruler which is longer.
Now, all things remain same. Just change the contact time. Okay, thank you. And since the former statement mentioned that the ball will bounce a bit, so when the ball reaches a critical height, will it still bounce a bit?
I mentioned that if the ball goes upwards, it was the observation noted caused by the restoring force of the ball, not that really bouncing off.
Okay. And when you calculate your theory, you use the area of your paper. So do you think the length and the width of the paper affect the same in this phenomenon?
I think it does affect it.
Okay, and you, yes or no?
Yes.
Hands up. So preparation time for the reviewer, 2 minutes. reviewer, yeah, please take the floor.
Honorable juries and fellow competitors, I'm the reviewer from Team Excelsior. Today I'm going to review problem 14, the ruler trick. So we will mainly focus on why will the rulers remain still on the table and the critical conditions under different circumstances. And this is a review for the report. He demonstrated placing a paper on a ruler and the ball falls on it and the ruler still remains on the table. And for the theory part, he mentioned the air pressure, torque, and the momentum. For the experiment, he done a lot of them, like releasing height and releasing mass. And for the pros and cons, he demonstrated the phenomenon well and explained it well, and done many parameters. However, his lack of theory line and didn't measure the air pressure, and he didn't analyze any critical conditions, and didn't consider the elastic coefficient of the ruler and the ball. And he detailed the theoretical derivation, and he has clear illustration. However, he is not suitable for some cases. And this is the advantage and disadvantage for the opposition. He noticed the lack of the explanation of how the air pressure works under the paper. And he also mentioned the boundary conditions of this phenomenon. And he noticed the lack of explanation on the contradiction between the theory and the data, since the reporter didn't have the theory line. And he discussed on the setup and the parameters in the theory. However, he made some discussion about the critical conditions and the velocity of airflow, which I think is quite important, and direction of the airflow, and also the pressure difference above and under the paper. And he didn't notice the velocity of the airflow. So for the first key discussion, it is about the deformation of paper. The opponent asks that if the paper jumps up, the phenomenon still happens. Why? And the reporter said it is because of pressure difference, and the reviewer thinks that it's because the volume under the paper increased so that the airflow will go into the volume under the paper so that the pressure will decrease and leads to the paper to balance the torque on the ruler. And the next one is the table material. The opponent asks that will the table material affect this phenomenon, and the reporter thinks that the thickness and other will affect. And the reviewer thinks that if your surface under the paper is plastic, it will have static electricity with the paper. So it might lead to a higher critical height. And for our question, I asked if the shape of the paper affects this phenomenon. And I think that if the paper can balance the ruler and it is still at the same area, then the result won't change. It will remain on the table or just fall off. And the opponent thinks that the shape of the paper will affect the volume. The reporter thinks it will make sure the edge are closed down. And the next question is the contact time. I asked if the acting time of the contact time point will affect the phenomenon. I think if the contact time is higher, then it provides more time for the airflow to flow in, so the critical height will be higher. And the reporter thinks that the lower contact time will lead to a higher critical height. And for the point base, they didn't talk about the qualitative explanation, and they didn't discuss about the releasing method since he used a tennis ball. And he didn't discuss the gas under the paper and different kind of gas, and also the phenomenal demonstration and the pressure.
So the concluding remark from the reporter.
So some of my concluding remarks, my theory is derived from the relationship of the torques on the ruler, and I showed that the phenomenon is caused by the air pressure through some initial observations, such as noting how noting that the weight of the paper is not sufficient to keep the ruler on the table, and I also checked the proportionality of the factors to make sure that it is caused by the atmospheric pressure. And although I did not test the hypothesis of causing change in the initial pressure, I believe that the differences in pressure would not impact the volume as much. I also agree that the material of the table material of the table would affect the force of the phenomenon by affecting how the shape and the volume underneath the paper would be formed and distributed. And I did test the inertia by comparing. I did compare the inertia and leverage of a ruler by varying the different ratios of hanging length. And I also discussed how different. I also how to look at contact time with using the same case with inertia. And I also noted how the shape of the paper would affect how the weight and how the edges are enclosed. And I also noted how most of the energy in the ball goes into the ruler upon collision. And finally, I must note that in discussion of this topic, volume of the paper will ultimately matter more than how the edges are formed, since the volume of the paper would directly relate to the force output, while how the edges are formed on the table are more related as a limiting factor to when the ruler would be when the ball would be able to hit on the table.
Okay, so now the question from the jury. Okay,
Okay, so I see we have examined several parameters for these experiments. I'm just thinking another parameter that was not investigated, which is the bending rigidity of the paper. So suppose you have several papers with different bending rigidity. So you do the experiment from small bending rigidity to large bending rigidity. So how would that change the result of the experiment? So let's start with the reviewer.
Can you explain?
Okay, so I'm just saying that there is one parameter for the investigate, which is the bending rigidity of the paper or the stickiness of the paper. So if you use many different kinds of paper with different stiffness of bending rigidity, so starting from the small bending rigidity to large bending rigidity, how would that change the result of these experiments? So we start with the reviewer example and then.
Okay. If the paper is more thick or is more stiffness, it's rigid, that it can bend really well. So when a ruler receives a force, it tries to lift up against the paper, so that because it is harder to lift up the paper, so the critical height will be higher.
For me, because like some of the paper will have better flexible. So if I make the paper become thicker, it still will attach to the table. So I'm going to see what kind of the paper. But if I'm dealing with same kind of the paper, and I think it will cause maybe some of the air is going down the paper because it is harder to bend. And it will cause when the ruler is flying up, the air will go in.
I think it will affect the shape that the paper would form when being lifted up. For example, a more rigid paper would form, for example, a single triangle, and not only this would increase the volume of the paper, it would also leave out one edge more open to air. But if the paper was less rigid, it would be able to break downwards and decrease the volume, but it will also ensure that all the edges are closed, preventing the air to rush to fill up the vacuum.
Okay. So other questions from the jury?
How to control the compacted time? How to control the compacted time because the ball falling down? How to control this time?
So the problem
in your part in the slide.
So like the problem with this is that I have to ensure that the ball has to be dropped in free fall. So anytime it's in free fall, it could be affected by some changes. So one way I would think of it is to put it through a tube and a low friction tube to make sure that when it falls down, it wouldn't be dragged by the tube, and just make sure that when it falls out and hits the ruler, I can at least measure the instantaneous velocity upon falling out the tube. But there are some issues such as the area being too small, the ball might fall the wrong way, or just making sure that the tube is the friction is too smooth.
So any other questions? Okay, please.
If you fold your paper, the same paper, but expose the tip of the ruler, How will it affect your result?
I think it would open up one of the edges. It would open up one of the edges and it would create the same effect as I mentioned earlier, which is it would increase the volume, but also allow air to rush in towards one of the edges and fill the vacuum.
And I also think that the volume underneath the paper will become larger, so the air will come in more easily.
And you say the folded.
Not cover the tip of the end of the ruler. Because they cover the whole part of the ruler on the table.
Yeah.
And the fold paper, you expose the tip.
For me, because when we are folded, they have like a line in here, and a line that we are folded in here, it is harder to bend. It will be harder to bend. So when the thing is like the ruler is flipping up, then that place, that slide is harder to bend. So I think it will also just like, yeah.
Okay, so it's almost time up. So during story time. Okay, so for the reporter, 6, 7, 6, 7, 8. Next, for the opponent, 6, 6, 5, 5, 5. For the reviewer, 6, 7, 7, 6, 8. Okay, so end Yannick's session.